Hi, everyone. Welcome to a special edition of GOCC where we have a talk from an expert. Today, we have Jim Propp from University of Massachusetts Lowell talking about counting tilings. But before we begin, we will review our guidelines. We are all learning. Everyone has something to contribute, and no one has all the answers. With that, please take it away.
Okay, thank you, Aditya. I really appreciate the invitation, and I appreciate the opportunity to interest some young people in this area, which I'm still very excited about. I've been working in it for 30 years. There are some great open questions that we don't know how to touch yet. So I'm hoping some of you will work on these problems, but I'll get to the open problems closer to the end. Is anyone here, did anyone here either go to my 2023 lectures or perhaps my lecture from 2 weeks ago? I gave a talk called How to Count Tilings. So this is sort of a sequel to that. There's very little overlap, and I certainly don't assume anyone went to that talk, but they're intended to sort of be a sequence. And when I post links to them, I'll link them together. Um, so here are the slides for the talk. They're already up on the web. Um, so what do I mean by tilings? Well, at the upper left, you see a picture of a tiling of a 2x6 rectangle using 2x1 and 1x2 rectangles as tiles. These tiles are called dominoes. This is a domino tiling. Um, Below that, you see a somewhat strange shaped region, but the tiles being used to tile it are rather nice. They're just unions of two equilateral triangles of the same length, side length, sharing an edge. And those are called lozenges. This is a lozenge tiling of a region. And at the bottom, you see a 4x4 square tiled with what are called four ribbons. So I should explain what a four ribbon is. On the next slide, you can see each domino is a union of two unit squares. Each lozenge is a union of two unit equilateral triangles. Each four ribbon is a union of four squares, but the rule is that you have to be able to march from unit square to unit square along the tile, either traveling to the right or traveling up. You're not allowed to go down or to the left. So you can see here each of the four tiles is following that rule. There's a right right and a right up and an up up and an upright. I'm not describing them properly. There's an arrow missing actually at the upper left. There's a mistake in the slide. So there should be an arrow coming in. Each of the tiles should have three arrows on it. I'll fix that when I post it. So that's the first mistake in the talk. If there are others, please point them out to me. Um, so we can ask, well, how many such tilings are there? So here I've erased the tilings. I've just left the unit squares or unit triangles in place. And the answer to the first problem, number of ways to tile the 2x6 rectangle with dominoes is 13. The number of ways to tile this odd-shaped region with lozenges is 14. And the number of ways to tile the 4x4 square with four ribbon tiles is 24. Any guesses as to patterns that these numbers might be part of? When you see the number 13, what does that make you think of? Aditya, you're muted.
Yeah, I wasn't going to say it out loud.
Um,
Fibonacci.
Yeah, the Fibonacci or Virahanka or Hemachandra or whatever numbers. Um, they actually came from enumerative combinatorics thousands of years ago. It wasn't about bunnies, it was counting verse patterns in Sanskrit. And then, Fibonacci got all the credit, but in fact, it's much older than Fibonacci. What about the number 14? This is a little more recondite. If I told you the number before this was 5 and the number after it was 42, would that set off any bells in anyone's head?
the Catalan.
Yeah, the Catalan numbers are the answer to this problem when you generalize it. And finally, here's an easier one. What does 24 make you think of in a combinatorial context?
4 factorial.
4 factorial, that's right. So here's the general fact. If you tile a 2 by n rectangle, the number with dominoes, the number of tilings is always a Fibonacci number. If you cover this sort of weird shaped region in the middle panel with lozenges, the number of tilings goes like the Catalan numbers. And if you tile an n by n square with n ribbon tiles, the number of tilings is n factorial, a nice fact I learned from Chris Moore. So one reason to count tilings is that you get nice formulas, and sometimes it's not obvious why the formulas are true. So it's a fun thing to work on just for its own sake as an interesting puzzle. So that's a large part of my motivation. So here's a region called an Aztec diamond, and we can look at domino tilings of it. And if we look at this particular region, well, let me describe what an Aztec diamond is. So this is an Aztec diamond of order 3. An Aztec diamond of order n consists of a row of 2 squares on the top, and then underneath it a row of 4 squares, and then 6 squares, and so forth, till finally you get to a row of 2n squares. Then you have another row of 2n squares. Here n is 3, so that's the second row of length 6. And then the lengths decrease by 2, and the rows are centered in this fashion, so you end up with a figure with a lot of rotational and reflectional symmetry. That's an Aztec diamond of order n. Here's an Aztec diamond of order 3, tiled by dominoes in one particular way. And if we count the number of domino tilings of the Aztec diamond of order 3, we get 64. What does that make you think of?
Maybe powers of 2?
Powers of 2. And that is right. That is a general fact. It was noticed by some physicists who didn't think it was even interesting enough to try to prove, because they wanted things with physical applications. But, you know, if you're a combinatorialist, you like to count things, and if you find an exact formula, you want to know why it's true. So Noam Elkins, Greg Kuperberg, Michael Larson, and I, a few decades ago, showed that for the Aztec diamond of order n, the number of domino tilings is always 2 to the power of n times n plus 1 over 2. So that's just a nice formula, you know. And here's an even older one, although when it was discovered by Major Percy McMahon over a century ago, he didn't think of it in terms of tilings. He used the language of plane partitions. I won't explain the dictionary that goes between those, but here's an example of a tiling of a regular hexagon of side length 3 with lozenges. And the number of tilings is exactly 980. Now, I'm not going to expect any of you to recognize that number. If you do, congratulations. But here's the general formula for the number of lozenge tilings of a regular hexagon of side length n. And one thing I want you to notice about this formula, aside from the fact that it's very simple, is that it's not even obvious that that product should be a whole number, because you've got a whole bunch of fractions. But in fact, it's always a whole number, and it's always exactly counting the number of lozenge tilings of a regular hexagon. So I think that's beautiful, and that's one of the reasons I do work in this area, is because of all these beautiful formulas that pop up. First, just empirically, and then you're able to prove them. So I gave a talk called How to Count Tilings a few weeks ago. The slides and the Zoom video are available, and I sketched 2 proofs of the first result about Aztec diamonds and 1 proof of the second result about lozenge tilings of hexagons. Those were purely combinatorial proofs. Today, I want to talk about higher powered methods that go beyond just the methods of combinatorics. Specifically, I want to use linear algebra. Now, in my talk 2 weeks ago, I also talked about tilings of regions I call benzels. So here's a benzel, and here's a tiling of it using regions made up of not 2 squares or 2 triangles, but 3 hexagons joined together in one of 2 particular ways, where they're either all 3 in a row or they form a nice compact triangle. So I will not talk about results like this these days, but I do want to mention that my most recent work is going beyond things like dominoes and lozenges to more general tiling problems in a sort of experimental math vein, just seeing which sorts of questions seem to have nice answers, and then when there's nice answers, trying to prove them. But a lot of the time when you try and solve counting problems like this, you just get a bunch of big numbers with no visible patterns, and you don't know what to do. And maybe it's a challenge for the future to find formulas for those cases, but I'm focusing on the ones where there are patterns that cry out for explanation. So our goal today is to count domino tilings of a 2n by 2n square in a way that's independent of n. So I'll show a couple of attempts which get us part of the way there, and then I'll show the thing that actually lets you prove an exact product formula for the number of domino tilings of a 2n by 2n square. Any questions yet? So let's start with counting domino tilings of a 2 by n rectangle. I'm going to call that number t sub n. You can show that it's the coefficient of x to the n in this generating function, 1 plus 1x plus 2x squared plus 3x cubed and so forth, which is given by the rational function 1 over 1 minus x squared. And the way you prove this is by showing that the sequence T sub n satisfies a second order recurrence relation. So if you've got a 2 by n rectangle and you want to tile it by dominoes, there are two basic cases for what you see at the far right of the rectangle. Either you see a single vertical domino or you see two horizontal dominoes. Now, in the first case, you basically reduce the problem of counting domino tilings of the 2 by n rectangle to the problem of counting domino tilings of the 2 by n minus 1 rectangle. And you know that there are t sub n minus 1 ways to do that. In the second case, you reduce the problem of counting the number of domino tilings of order n to the problem of counting the number of domino tilings of order n minus 2. And that's given by t sub n minus 2. So we have the recurrence relation t sub n equals t sub n minus 1 plus t sub n minus 2. And when you use standard technology for solving linear recurrence relations by way of generating functions, you find you get this rational function of x. So more generally, for any fixed m, the number of domino tilings of an m by n rectangle, called a t of m comma n, is the coefficient of x to the n in a rational generating function. So each value of m determines a rational generating function. For m equals 2, it's this. For m equals 3, it's something else. For m equals 4, it's something else. But for each fixed m, if you let n vary, you're going to get a rational generating function, or putting it differently, the numbers t sub m comma n, as m is fixed and n varies, will satisfy some sort of linear recurrence relation, which seems like a smart way to proceed. Let me describe the idea of the proof. We want to keep track of the number of all ways to tile an m by n rectangle with lots of kinds of ragged right edge. And then we're going to set up a joint first order recurrence relation linking all of them. The reason we do that is as soon as we get to considering, say, a 3 by n rectangle, there's more than just the case where you have a single vertical domino or you have 3 horizontal dominoes. You could have a single vertical domino and a single horizontal domino sticking out to the left. So if you want to get a recurrence relation going, you really have to consider more possible subregions that you can encounter as you take bites out of this region going from right to left. So you're going to set up a bunch of supplementary counting problems and solve them all simultaneously with a system of recurrences. This system of recurrences can be encoded as a recurrence for a sequence of vectors where each vector is obtained from the one before by multiplying it by a matrix M, where M is called a transfer matrix. And the matrix entries M sub ij, where I and j are counting the different possible ragged patterns for the right edge, gives the number of ways to extend a tiling of a near rectangle of length k and edge type I to obtain a tiling of a near rectangle of length k plus 1 and edge type j. The problem is the number of edge types grows exponentially. So this may not be a practical method of doing things. Now it appears that when I claim that it grows exponentially, that there's an exact formula for the degree of the denominator, which is the same as the order of the recurrence. So when this rational function is expressed in reduced form, the denominator always appears to be of degree 2 to the power of the floor of m plus 1 over 2. And Jeff Ligarius proved this when m plus 1 is an odd prime. So if, for instance, we look at the integer sequence that counts the number of domino tilings of a 100 by n rectangle, as n goes from 0 up to infinity, it satisfies a linear recurrence of pretty whopping large order. In fact, looking at it quickly, million, billion, trillion, quadrillion, I had to actually count the groups of 3 digits to see that it was about 1 quadrillion. Okay, so that's not going to be a good approach for this problem, applying a linear recurrence relation after the first 1 quadrillion terms. Just do the first 1 quadrillion cases honestly and then use the recurrence thereafter. That's not a way to solve this problem, to say compute the number of domino tilings of an 8 by 8 square. Now there is a nice way for a 7 by 7 square or a 9 by 9 square. Well, of course there is. There are 0 tilings of those regions because they have odd areas. But actually, if you remove one corner of an odd by odd square, now it has even area. And now there's a nice way to compute the number of domino tilings of an odd by odd square with a corner removed. And that uses a bijection with spanning trees of an n by n grid graph. So let's put a dot in every fourth location, starting at the upper right with the removed square, and going over every second column and every second row. And now what I'm going to do is connect each dot with some other dot by looking at the domino that covers it and going in the direction of the other square. So for example, look at the upper left dot. It lies on a horizontal domino. So we could draw an arrow from the center of the upper leftmost square to its neighbor to the right. But let's continue going in that same direction until we arrive at the second dot in the top row. What covers it? A horizontal domino going to the right. So the next arrow also goes to the right. So now we're at the third dot in the top row. Now that one is covered by a vertical domino that goes down. So we connect that dot downward to the dot below it. And then you can keep following it around and you see that all these arrows point from one dot to another dot, except the dot at the upper right, which isn't covered by any domino at all. And what we end up with is a directed spanning tree in which every vertex has a single arrow coming out, except for the one at the root at the upper right. And if you follow those arrows, you always wind up at the root. So I'm not going to prove this for you, but this is a bijection. You can actually recover the domino tiling from the spanning tree. This is very much in the sort of spirit of the combinatorial constructions I talk about in my first lecture, but I did say I'm going to focus on linear algebra today. The linear algebra comes into play when we ask, okay, how do we count the number of spanning trees of the n by n grid graph? Oh, one more step I should mention is that although I've drawn the arrows here, we can actually suppress the arrows because we can always reconstruct how the arrows point by just from every vertex following the path, the unique path that leads to the root. So I now
Can I
have
interrupt
sketched
you?
for you.
Sorry, Jim, to ask you something.
Yeah.
Can you go back one slide? Oh, so where do pairs of perfect matchings of the grid graph appear in this picture, or do they not appear in this picture?
We don't have, it's not a double dimer model. It's not a pair of perfect matchings. It's just one perfect matching of this grid graph indicated by
Okay.
the dominoes. So yeah, I haven't talked about perfect matchings yet. That's going to come up in a bit.
Okay.
Right now I'm just doing tilings. So we put in the dots in just a quarter of the cells, and then we draw a spanning tree there, and it's directed, but it turns out that from this graph, not only can we reconstruct the orientations of the edges and thereby reconstruct how we cover each of these dots with a domino, but we can also uniquely reconstruct where the other dominoes go, the dominoes that don't contain a dot at all. So for example, if you look at this square, it's sort of isolated. So the only domino, once we put down this domino and this domino and this domino and this domino and so forth, the only place to put a domino covering this square is to go to the right. Now this domino, if we hadn't looked at this domino, we would say, gee, this square has two neighbors, a neighbor to the left and a downward neighbor. But once we know that this domino is forced, then this domino is also forced to be present. And in fact, you can work in the dual tree, for those of you who know that concept, and basically view the dual tree as being rooted also at a vertex in the sort of outside face here, and you can basically reconstruct the whole tiling from just this undirected spanning tree. Not proving anything here, I'm just trying to raise people's curiosity and sort of show you what you can look forward to learning about if you choose to explore this area. So now the question is, how do we count spanning trees? Well, we use something called the matrix tree theorem. This works for any simple graph, not necessarily planar. So given a simple graph G with vertices V1 through Vn, so no self-loops, no multiple edges, we'll let a sub ij, for I and j going from 1 to n, be -1 if vertex I and vertex j are adjacent, and we'll let a sub I be the degree of I if I equals j, and 0 otherwise. There's a mistake there. Oh, no, that's not a mistake. Yeah, if j equals I, we're looking at the diagonal entries. I could have just said, yeah, that doesn't make any sense to me. Yeah, I don't know what I mean, and 0 otherwise.
I think you mean 0 if I is not equal to j and vi and vj are not adjacent.
Oh, yes. Yeah. Yep, that's what I meant. Thank you. Yeah. So then, for all I going from 1 to n, by the way, if you look at the n by n matrix, it has determinant 0. So its determinant doesn't tell you anything. But if you cross out the ith row and the ith column for any choice of I, and take the determinant of that n minus 1 by n minus 1 matrix, it's the number of spanning trees of the graph. That's the matrix tree theorem. So for instance, to count the domino tilings of a 3 by 3 square with an upper right corner removed, this bijection, due to temporally, gives us spanning trees of the 2 by 2 grid graph. Now we can easily count the number of spanning trees of the 2 by 2 grid graph, so you just see them right there. So we've got basically 4 vertices and 4 edges, and a spanning tree just removes one of the 4 edges. There are 4 ways to do that. The more labor-intensive way is to set up the 4 by 4 determinant, cross out a row and a column, and look at a 3 by 3 matrix determinant and get the answer 4. But these two approaches scale differently. Drawing all the possible pictures does not scale well. Evaluating an n by n determinant, or even an n squared by n squared determinant, if we're looking at, an n by n graph with n squared vertices, it's still going to scale better, especially if there's something systematic you can say about its spectrum, which in this case you can. So by taking the spectrum of the matrix, you actually take the full n by n matrix. It has determinant 0. That's because it has an eigenvalue 0. But 0 is a simple eigenvalue. Multiply together all the non-zero eigenvalues, you get the determinant of the matrix you get when you delete a row in the corresponding column, and we get this product formula for the number of domino tilings of 2n minus 1 by 2n minus 1 square. I should have said square. I wrote rectangle. That's another mistake. With a corner removed. And that's given by this double product of trigonometric expressions. So whether you view that as a nice formula or not depends on how much you like trig functions in your products, but it's definitely explicit and it's definitely effective. And this bijection has been generalized. You can see the article by Kenyon et al. From 2000 and Kenyon and Sheffield in 2004. This is a good time for me to pause for questions.
Yeah. Hi, Jim. I wonder if you could sketch how you do that. How do you work? Do that? Get from the how you characterize the eigenvalues and get that formula.
It's been years since I've looked at those details, so I'm not going to try to wing even an overview of that, except later on I'm going to give a link to an article I wrote, which basically does a similar analysis for counting domino tilings of the 2n by 2n square, and the same method works there. You view it as kind of like a Laplacian, and the eigenvectors you think of as being eigenfunctions in a certain discrete setting, and then you just compute them explicitly. So that's the best answer I can give you. Other questions?
Because of its similarity to the Castellan formula, is there a way to use the same proof techniques in both, or like go between each other?
Well, sort of, yes, in the sense that once you've reduced it to a matrix problem of computing eigenvalues, then you can use, eigenfunctions on a discrete graph kind of thing, and the symmetries of the graph help you. But in terms of an underlying connection between Castellan's method and Temperley's method, I don't know. I don't know if there's a way of seeing them as being special cases of one approach. One reason I tend not to think so is that Castellan's method, as we'll see, involves these extra fiddly sign factors and also depends on the planarity of the graph, whereas counting spanning trees, the matrix tree theorem doesn't require any special structure for the graph. So that makes me skeptical about there being a deep connection, but there might still be one. I just don't know. Other questions?
Thank you.
Okay, so I'll move on now. Let me talk about the Lindstrom's lemma approach. So here is a rhombus tiling of a hexagon. I'm going to break the symmetry by putting dots in the midpoints of the horizontal edges in this picture. Okay? And now I notice that there are two kinds of situations that a dot could be in. Like some dots are in the middle of a tile, and other dots are on the boundary of a tile. But when there's a dot on the boundary of a tile, there's another dot on the opposite side of the tile. And so you could join them by an edge. Now, that dot has to itself be connected to another dot, which has to be connected to another dot until finally you arrive at the top edges of the graph, and then the picture, you can't go any further. So what you get from this is a bunch of paths connecting S1, S2, and S3 to T1, T2, and T3. But in fact, they can't cross each other either. So you get 3 non-intersecting lattice paths from S1 to T1, S2 to T2, and S3 to T3. And then you get some dots that don't belong on any paths at all, and those are the dots that lie in the middle of a tile. So you can reconstruct the tiling from the paths. The paths tell you where to lay down these non-vertical lozenges, the ones that have a horizontal side on the bottom and on the top. And then once you put those down, you're forced to place the other lozenges to cover those other dots. So you've lost no information when you replace the tiling by a family of non-intersecting lattice paths. So how do you count the number of lattice paths? Well, again, with linear algebra. So here's a general fact. Suppose we're given an acyclic finite-directed graph G with n source nodes, S1 through Sn, and n terminal nodes, T1 through Tn. So going back to this picture, you should imagine that all the possible directed edges have been drawn in. So from S1, we can go up and to the left, but from S1, we can also go up and to the right. And from this vertex, we have edges going from here to here and from here to here. So all those edges are there. I should have probably included a slide showing those too. So we have n source nodes and t terminal nodes, and I'm going to let a sub I j be the number of paths from s sub I to t sub j. But suppose, as in this case is true because of topological reasons, or for any other reason, suppose that the only way to have n non-intersecting paths joining the initial nodes to the terminal nodes is to join Si to Ti for I going from 1 to n. So in this case, you couldn't have S1 going to T2 and S2 joining to T1 because of the combinatorial topology of the picture. Then the determinant of the matrix whose entries are A sub ij, called the Lindstrom matrix or the Gestel-Viennot matrix after the combinatorialists who rediscovered Lindstrom's lemma, is the number of families of n pairwise non-intersecting lattice paths from the source nodes to the terminal nodes. So when I say non-intersecting, I mean non-intersecting in the strong sense, no vertices or edges in common between the paths. Here's a special case n equals 2, with just 2 sources and 2 targets. So the number of pairs of non-intersecting paths joining S1 to T1 and S2 to T2 is equal to this 2 by 2 determinant, where A11 counts the paths from S1 to T1, A22 counts the number of paths from S2 to T2, A12 counts the paths from S1 to T2, and A21 counts the paths from S2 to T1. So what is the idea of the proof? And the idea is to use this technique called path switching. So the idea is that this thing overcounts. A11, A22 overcounts the number of non-intersecting paths because A11 is the total number of paths from S1 to T1, A22 is the total number of paths from S2 to T2. So this product is an overestimate. One way we can subtract off exactly what we want to, namely the intersecting lattice paths, is by counting all these pairs of paths. Well, why should that be? Well, let's look at a red path here from S1 to T1 and a blue path here from S2 to T2 that intersect. Let's find the first point of intersection. So there's a place where they intersect. And what we're going to do is we're going to take all those blue edges from that point in the path and recolor them red, and all the red edges from there to T1 and recolor them blue. What do we get now? Now we get a red path from S1 to T2 and a blue path from S2 to T1. It looks like we've lost some information here, but we haven't, because given this picture, if we want to recover the picture on the left, just find the first place where the red path and the blue path intersect and do this recoloring again, and you'll reconstruct the picture on the left. So that's why A12 times A21 is exactly the overcounting that we did when we looked at A11 times A22. And this generalizes to values of n larger than 2, but the basic idea of the proof is the same. Any questions about this?
So is this a reflection involution?
Yes, it is.
Oh.
Interestingly, it wasn't a combinatorialist who came up with it. It was a probabilist. Lindstrom was studying Brownian motion when he came up with this. And the Aztec diamond thing, as I said, was discovered by physicists. So sometimes there's stuff outside of combinatorics that's really interesting combinatorially if you happen to read enough things. And then you end up rediscovering it if you haven't read enough things. So here's an application of Lindstrom's lemma. The number of lozenge tilings of the hexagon of side length 3 is given by this 3 by 3 determinant of binomial coefficients. So for instance, if we count the number of paths joining S1 to T3, well, that's going to be a path that has to go 1, 2, 3, 4, 5 steps up and right and 1 step up and left. So that's 6 choose 1. So there you see 6 choose 1 as the number of paths joining S1 to T3. And these are all binomial coefficients, and if you're handy with determinants of binomial coefficients, then you can derive the product formula from them. But, the point is, this is good for calculations, even if you don't know how to generalize to all values of n. You can do something similar with domino tilings of a square. So this is a trick invented by Dana Randall. So now, just to vary things, I'm going to put dots in the middle of vertical edges, but not all the vertical edges, only half of them. So you can see the sort of alternating pattern I use for assigning dots to some vertical edges and some not. Excuse me, I need to swallow. So now, once again, some dots are in the middle of a tile, and other dots appear 2 places on diametrically opposite sides of a tile. So you can join those up. So we have the points S1, S2, and S3. And in each case, once you travel along a path edge, you have to keep going until you arrive at T1, T2, and T3. And for combinatorial topology reasons, these paths cannot intersect with each other. And once you've put down all the tiles associated with these segments, the rest of the tiling is forced. So there's a bijection between tilings of the 6 by 6 square and families of non-intersecting lattice paths in this graph. Let me take a smaller case. So here we're counting tilings of the 4 by 4 square grid. So now we just have 2 sources, S1 and S2, 2 targets, T1 and T2, or 2 terminals, T1 and T2. And if we look at all the edges we could draw, they're all directed edges. I've left out the arrows. They go from left to right. And these are all the directed edges you can have. So for instance, from S1, there are 3 edges coming out corresponding to the 3 ways you could cover this square. You could cover it by a horizontal domino, or by a vertical domino going up, or a vertical domino going down. So now we can count non-intersecting lattice paths using Lindstrom's lemma. So here I'm showing for each vertex how many paths there are from S1 to that vertex. So for example, in this circle, there's only one way to get from S1. In this circle, there's only one way to get to S1. This circle, there are 3 ways to get to S1 because you get there from here, or from S1 itself, or from here. It's like a Pascal's triangles recurrence where you just add a bunch of numbers to get the new numbers. And finally, at the right, you get 4 plus 3 plus 5 equals 12. And 6 equals 5 plus 1. So those count the paths from S1 to T1, that's 12, and S1 to T2, that's 6. And we can also count paths from S2 to T1, that's 6, and S2 to T2, that's 6. So taking the 2 by 2 matrix determinant, we get the determinant of this matrix, which equals 36. So using linear algebra to count those tilings. So now I want to talk about the thing that actually is going to give us an exact formula for the number of domino tilings of the 2n by 2n squared generally. Good time for me to pause for questions and also see how I'm doing for time. It's 12:38. I should be able to finish by 1. Any questions? Okay. So I'm going to view this domino tiling as a perfect matching of a graph where the nodes in this graph correspond to the centers of the squares in this graph. 2 squares sharing a domino corresponds to 2 vertices being connected by an edge. And likewise for the lozenge tiling picture on the right. And this next picture shows all the possible edges we could have, where I've bold-faced the edges we've chosen to have. And so counting the domino tilings of an Aztec diamond is equivalent to counting the perfect matchings of this graph, the dual graph shown on the left. And likewise, counting the lozenge tilings of a hexagon is equivalent to counting the number of perfect matchings of this kind of hexagonal graph, lattice of hexagons shown on the right. A little bit of cultural terminology. Another word for a matching is a perfect matching. In this context, I'll always mean a perfect matching. Sometimes people call it a one factor because it's a subgraph in which each vertex has degree 1. It's also called a dimer cover. And in the chemical literature, when the graph is a benzenoid, which is a bunch of hexagons stuck together, matchings are also called Kekule structures or resonance structures for reasons I won't have time to go into. So, lovely trick before I talk about counting is counting mod 2. So when does a graph have an even number of perfect matchings? Is there a nice way to tell? Lowell showed that a graph, any graph at all, doesn't have to be planar, has an even number of perfect matchings if and only if there exists some non-empty set C of vertices such that every vertex in V is adjacent to an even number of vertices in C. Why should that be true? Let's let A be the adjacency matrix of G with rows and columns corresponding to the vertices V1, V2, etc. of V, and with the ijth entry equal to the number of edges joining Vi and Vj. So for simple graphs, it's going to be 0 or 1. Oh, wait a second. Did I say number of vertices or number of edges? Yeah, I think I want it to be a simple graph, so I believe that's again a mistake. Did I say it's a simple graph? No, I didn't. Okay, I'll have to fix that. So here's the proof. So the matchings of G are going to correspond exactly to the non-zero terms in the expansion of the determinant that are symmetric with respect to the main diagonal. Because remember, in a perfect matching, a contribution to the determinant is just a bunch of entries where for each I, you have you pair the ith row with the pi 1th column, the second row with the pi 2th column, and so forth. So each permutation, each of the n factorial permutations of this n by n matrix counts a function from the vertex set to itself, but it may not be an involution. So the right way to think about perfect matchings in this context is terms in the expansion that are symmetric with respect to the main diagonal, because then we're looking not just at a function from the rows to the columns, or from the vertices to the vertices, but a function of order 2 that's symmetric with respect to the main diagonal. So vertex I, if you have a 1 in the ith row and jth column and a 1 in the jth row and the ith column, that's the kind of thing that's contributing to counting the perfect matchings of the graph. Now, there are other terms, and they may be non-vanishing, but they will cancel in pairs when you work mod 2. Because after all, this matrix is symmetric. I didn't say that, but this is a symmetric matrix. That's important. So the number of matchings is even if and only if the determinant vanishes mod 2, vanishes over the field with 2 elements. Now, general linear algebra over an arbitrary field tells us that this occurs if the rows are linearly dependent mod 2. Well, what does that mean? That means you can choose a subset of the rows, a linear combination of the rows. But in mod 2, linear combination means you use some and you don't use the rest, because the only coefficients are 0 and 1. So linear combination just means an additive combination of a subset. So you take some non-empty subset of the rows, must sum to the 0 vector. So summing the rows of A that correspond to the vertices of some non-empty set C gives the 0 vector. But what does that mean combinatorially? That means C as a subset has the property that every vertex in V is adjacent to an even number of vertices in C. I have no idea how he came up with this, but it's no longer an isolated result because Barkley and Liu came up with extensions of Lovatz's approach and Lovatz's results. So all the red text in these things are live links in the PDF, so you can always learn more by going to the PDF and clicking them. But now we really want to count the number of perfect matchings of a graph. Well, for a general graph, you can't do that. It's sharp P complete. But if you've got perfect matchings of a bipartite planar graph, G, with 2 n vertices, n black and n white, well, it's always equal to the permanent of an n by n bipartite adjacency matrix, A, whose ijth entry is 1 or 0, according to whether the ith black vertex is adjacent to the jth white vertex or not. So now you've got an n by n matrix instead of a 2n by 2n matrix. But permanents are hard to compute, so this doesn't seem like it's progress. But if the graph is planar, then Castellane showed that you can monkey with the signs of the non-zero elements of A, or more generally replace them by complex numbers of norm 1, in such a way that in the resulting matrix K, all the non-zero contributions to the determinant interfere constructively so that the determinant of K is the number of matchings up to sign, or up to modulus, okay? Sometimes you don't even have to monkey with the entries. Like for instance, let's take the cycle of length 6, or more generally, length 2 mod 4. If you look at the adjacency matrix for this matrix and take its determinant, you get 2, which is the number of perfect matchings of this graph, because the non-zero contributions to the determinant all add constructively. If you try to do this with a 4 cycle, or the 8 cycle, or the 12 cycle, you'll get destructive interference between the two perfect matchings. But change a sign, suddenly they're constructively interfering. So here's 2 by 2 matrix where we've changed a sign. Now the determinant is exactly 2. And Castellane showed you can always do this. There's a way to assign signs to the edges so the product of the signs around a face is +1 or -1, according to whether the number of edges around the face is 2 mod 4 or 0 mod 4, and this gives a matrix whose determinant has magnitude equal to the number of perfect matchings of the graph. Great news. So, a lot of details swept under the rug here. In the case of the 2n by 2n grid graph, or more generally the 2m by 2n rectangle, you can work out the eigenvalues of the Castellane matrix, see Propp 1997, and show that the number of domino tilings is given by this product. Okay, the product of the eigenvalues of K. Any questions about that? Okay. So now I want to talk about very recent work. So to move beyond dimers, covers by trimers, tetramers, etc. So you've got a graph, you might want to have, triples of vertices where A is joined to B and B is joined to C in some fashion. You want to cover the graph with those, something like that. We're going to either need more ideas or find computational tools that suggest patterns that will then goad us into coming up with the new ideas, because the patterns we find will be so intriguing, we just have to work harder and think harder to find the ideas we need. So how do we find the patterns that will make us do the work? By suggesting that our work will not be in vain. So you could do brute force enumeration of tilings, but that won't get you very far, because some of these patterns don't emerge until you're looking at tilings where the tiling problems where the number of tilings has 20 digits or 30 digits. How are you going to ever count those? Well, you have to be smart. So David Desjardins is smart, and he wrote a smart program called Tiling Count. And when the conditions are right, it can do smart force exact enumeration of tilings of regions with up to a Google tilings. Okay, and actually I should probably include a link to his video in which he explains his idea, because I really want more people to learn his method and implement it, not just in C++, but inside Sage Math or inside Mathematica, so people can use it as an engine for doing other sorts of things. Now, I've done lots of experiments with tiling count, and most of the time when I vary the tile set in the region being tiled, I get an integer sequence with no detectable nice properties, which may not mean there's nothing there. It may mean I just don't know how to find what's there. But there are intriguing exceptions where even I can see some interesting patterns. So let's look at tilings of the 2n by 2n square by dominoes and dominoes and 2 by 2 squares. So here you see a mixture of dominoes and 2 by 2 squares. Every 2 by 2 square can be tiled by dominoes in 2 ways, so we're not moving that far away from counting domino tilings. But there's no obvious correspondence with any kind of multiplicity between these guys and domino tilings. This is not just the number of domino tilings times some extra factor or divided by some extra factor. This is a genuinely different problem, but it feels similar. Look at these numbers. Anyone notice anything about these numbers? Someone other than Aditya. And don't be afraid to state obvious things. Or Seth, someone I haven't heard from yet.
The log grows exponentially.
Yeah, they're sort of growing. Actually, the log is growing quadratically, and you can get quadratic exponential upper and lower bounds for the number of tilings. So something else I want you to notice.
Someone mentioned something in chat. They said that they're all odd.
Oh, I can't really follow the chat. Let me view that. Yes. Let me see what else I missed. No, see, I'm in full screen, so I can't see the chat. So
don't worry, we'll let you know if there's anything.
Thank you. Yeah, if there's anything in the chat, someone should please let me know. Yes, they're all odd. Okay. Oh no, now I've lost, I think I have to go back. to zoom, and then I have to go back to preview.
We still see
No.
your shared screen.
You
But
do?
yeah. But
Um,
perhaps you don't see it. That's what
well,
I'm-
but you're seeing my reading list now, right?
no, we still see your slides just as before.
Okay.
Mhm.
I think your screen is different, but we're still seeing the preview. So you just need to go
Okay,
back.
now I can see the preview too.
Perfect.
Okay.
Okay.
Oh, shoot. I think I have to stop sharing and then restart the share.
All good.
No, I've lost control of.
Yes.
Okay. So anyway, yes, these numbers are all odd. They don't seem to exhibit any nice patterns mod 3, but if you look mod 4, it goes 1, 3, 1, 3, 1, 3, 1, 3, etc. Mod 5 doesn't show us anything. Mod 6 won't because mod 3 doesn't. Mod 7 doesn't, but mod 8 shows 1, 3, 5, 7, 1, 3, 5, 7, 1, 3, 5, 7. So there seems to be something special about powers of 2. And in fact, if we sort of look at these repeating blocks for mod 16, we have 1, 3, 5, 7, 9, 11, 13, 15, which seems especially nice. Actually, for mod 32, it doesn't just count up from 1 to 31 by odd numbers. So that pattern breaks. But what does seem to be true is if we let g of n be the number of tilings, oh, there's a typo, tilings plural, of the 2n by 2n square by dominoes and 2 by 2 squares, and we fix k, then if we look at things modulo 2 to the k, it's periodic. More specifically, if n and n prime are congruent mod 2 to the k, then g of n and g of n prime are congruent mod 2 to the k plus 1, which means that the repeat period is doubling. It's always a power of 2. So mod 32, it would repeat with period repeat length 16, and so forth. So one way of saying this is that the function g is uniformly continuous with respect to the two-adic metric. But even more seems to be true, because if you look at these repeat blocks, it's hard to see mod 32, the full repeat block, but if you start from the middle of the repeat block, so 31 and 17 should be the middle of the repeat block, 31 plus 17 is 48, that's divisible by a pretty big power of 2. So in fact, on the assumption of two-adic continuity, let's let g hat denote the unique two-adically continuous extension of g to the two-adic integers. Then it appears that for all two-adic integers n hat, if we take g hat of 1 minus n hat, we get the negative of g hat evaluated at n hat. That's this property that if you add them in opposite pairs, they sum to 0 modulo some large power of 2, which means they're negatives of each other. So I conjecture this in a 2023 article. Now you may be wondering, why would I have ever thought to look at these numbers, mod 4, mod 8, mod 16? Well, they're odd, so since they have a nice pattern mod 2, you might think natural to look mod 4. But in fact, I was really motivated by an old result of Henry Cohn. So this is a neglected quarter-century-old result. Write the number of domino tilings of a 2n by 2n square as 2 to the nth power times the square of f of n, which it turns out you can do for an odd integer valued function f. This was known before Cohn. But Cohn got some information about the function f that wasn't known before. He showed that the function f is uniformly continuous with respect to the two-adic metric, and its unique extension to a function from the two-adic integers to itself satisfies a more complicated kind of reciprocity or reflection property, that f hat of negative 1 minus n hat is sometimes f hat of n hat and sometimes negative f hat of n hat, according to the congruence class of n hat mod 4. And the way Cohn proved these results was by using the explicit product of eigenvalues formula for the number of domino tilings of a 2n by 2n square. So the only route we know for explaining phenomena like this uses linear algebra. So this makes me think maybe there's something analogous to Castellan's formula for counting domino tilings of regions that also applies to counting tilings of regions with dominoes and 2 by 2 squares. Now, that's sort of a wild guess, but that's the only way I know of proving Cohn's result. So maybe that suggests that there's hope, that there's an extension of linear algebra methods to apply to tilings of regions by dominoes and 2 by 2 squares. But this is not all. Here's another kind of tiling problem we could look at. So now we're going to tile 2n by 2n squares with t-tetrominoes, made of 3 squares joined together in this fashion. So as I said, when you do these problems, big numbers you tend to see big numbers displaying no patterns when you count tilings. But here you do see patterns. One really nice pattern found by Korn and Pack is that this counting problem is connected to the Tut polynomial. So if you take the n by n squared grid with n squared vertices, call it L sub n comma n, that's a graph, and you evaluated its Tut polynomial at the value 3 comma 3, the Tut polynomial has 2 variables, so you replace them both by 3, that's the number of t-tetromino tilings of a 4n by 4n square. In fact, I don't know if they proved this, but the number of tilings is always divisible by 2 to the n. So let's let h of n be 2 to the negative n times the number of tilings. Empirically, I find it's always an odd number. If you look at it mod 4, it goes 1, 5, 5, 1, 1, 5, 5, 1. Look at it mod 8, it's 1, 5, 13, 9, 9, 13, 5. Well, I wasn't able to get the next term, but I'm guessing it's going to be a 1. And looking at the data, I think the 2-added continuity and reciprocity results hold in this case as well, only now with h hat of 1 minus n hat equals h hat of n hat. Okay? But there's more. Let's count the number of ways to tile a 2n minus 1 by 2n minus 1 square using 2n squared minus 2n dominoes and a single 1 by 1 square. So remember, this square has an odd number of tilings, has an odd number of squares, so you can't tile it with dominoes. One approach we took to getting a tractable counting problem was to just take a specific square away. But now let's take away any square, any single square. And let's count all the ways to tile the complement of that 1 by 1 square with dominoes. Well, it has to be of the right color class. It has to be of the same color class as the upper corner. Otherwise, you're not correcting the color imbalance between white squares and black squares. But if you take this number and divide that number by 2 to the n minus 1, you get numbers that are always 1 mod 8, alternate between 1 and 9 mod 16, displaying patterns mod 32. Now you could use Temporally's method to count these tilings, but now each enumeration is going to be a sum of quadratically many determinants because each of the places you remove that single 1 by 1 square corresponds to a different domino tiling problem of tiling the complement. So yes, you're doing a perfect matching of the bipartite planar graph, but there's, a lot of them to add up together, but add them up together, get these nice numbers. So this is probably the most approachable of the tiling problems I've shown because at least you have a handle on the problem with linear algebra in terms of adding together a bunch of related determinants. So this is probably the easiest of them, but I really don't know. The moral is that there's a lot more work to be done in this area. I hope some of you will do it. If you're interested in learning more, this talk draws largely from the first 2 of my 3-lecture series, Combinatorics and Exact Enumeration in Dimer Models, from August of 2023, presented at the ITS Summer School on Dimers. Actually, the first place you should go is the talk I gave 2 weeks ago, where I had links at the very beginning, because that gives the combinatorial methods as opposed to the linear algebra methods. Slides from my 2023 talks are all available, along with a Zoom recording of my 3rd lecture. The first 2 Zoom lectures were on the cloud, and then they disappeared before someone thought to grab them off the cloud. So now they're gone forever. So my advice to you is don't let this happen to anything you care about. Something's on the cloud, grab it before it disappears. Thank you for coming. Thank you for listening, and I'll take more questions now.
Thank you so much for the talk. Yeah, the floor is now open for questions. If anybody wants, you can unmute yourself and ask.
Or could someone read to me what's in the chat? I see there was something added to the chat, because now there's a red 3.
Somebody's leaving and they said, thanks so much for the talk.
Oh, okay.
Yeah. So when we were doing that thing about changing the signs to make a determinant and making the permanent into a determinant, that I believe does indeed take lesser effort to figure out what the signs are than to just compute the permanent?
Oh, yes, absolutely.
Okay.
There's a very simple recipe. It's probably linear time in the area of the region. It's just, marching around. Like one thing I didn't mention is for the case of the 2n by 2n grid graph, what is the sign pattern that works? And the answer that I prefer is don't use plus ones and minus ones. Put I, square root of minus one, on every vertical edge in the graph. Because then if you look at the product of the weights around any force cycle, it's 1 times 1 times I, 2 horizontal edges and 2 vertical edges. Then the product is minus 1, and it's more symmetrical. So that leads to a conceptually simpler solution than having a less periodic pattern for the weights for the edges.
So the point there is that, in special, it's in matrices with where there's a structure to the non-zero elements, you could, convert the permanent to the determinant by putting in the appropriate complex numbers.
That's right. And the special structure includes sparsity. That's crucial.
Oh, I see. Is there any more general characterization of when that's possible? Or some theory that applies to this? Or
I know people have done work in this,
yeah,
including some people in computer science. So physics and computer science, people look at these sorts of things. It's been over a decade since I've looked at that, so I couldn't tell you, but maybe offline I'll ask some of the people I know who might know the details, and I could, forward you that information. But I should
okay.
mention that the graph doesn't have to be bipartite. And it doesn't have to be exactly planar. Like if you have, say, a graph on a torus, then you can use a variant of the permanent determinant trick where you express the answer as a sum of 4 determinants. And in general, I think the rule is 4 to the power of the genus of the surface gives a bound on the number of determinants you need.
So are we're talking about the adjacency matrix?
Yes. The
And
adjacency
so if the graph is planar, you could do this
with one determinant if it's bipartite. If it's not bipartite but it's planar, you can use what's called a Pfaffian instead of a determinant.
Oh yeah, sure. Yeah.
And then if you've got something that's not bipartite and not planar, as long as it's on the surface of small genus, you can use linear algebra for that as well.
Oh, cool. Yeah. Of course, another question. In your travels, in this, like from your 1997 paper and Castellian's work, have you seen much appeal to the Fourier analysis theory, discrete Fourier analysis?
I haven't seen a lot of it. That doesn't mean it's not out there for exact solutions to these things. I think physicists sometimes use approximately true Fourier methods to draw non-rigorous conclusions about statistical mechanics models. But I've never gone that route. I've never looked into that literature, so. Other questions?
There is a question in the chat. What is the motivation for using p-adic evaluations slash functions? And this is coming from someone who's not familiar with this area.
Yeah, just because it's patterns. Like if you just were to count something that God doesn't want you to count, then you wouldn't expect there to be any patterns there. It would just be big numbers, and you just can't really predict their parity or anything nice about them at all. But on the other hand, if you see big numbers that exhibit some sort of patterns, whether it's the fact that they're perfect squares, like I sort of breezed over this, but someone who had access to a computer, centuries ago, could have noticed that the number of domino tilings of a 2n by 2n square is always either a perfect square or twice a perfect square. In fact, it's always equal to 2 to the nth power times a perfect square for the 2n by 2n board. That would have been an example of a pattern that cries out for explanation. Someone could have even done it by hand, like they look at the 4x4 board, it is 36 domino tilings. Is it a coincidence that it's a perfect square? 6x6, it's twice a perfect square. 8x8, again, it's a perfect square. Someone centuries ago could have come up with methods for doing by hand counting in the course of a day, counted the domino tilings of the 8x8 square and said, it's a perfect square. There's something to figure out and understand here. And maybe they would have found Castellan's method a century before Castellan. Who knows? So one of my approaches to finding new combinatorics is just seeing what are the things that we don't understand at all, but where we can use computers' power to find data that might exhibit patterns. And then we say, wait a second, there's got to be a reason for this pattern, and then focus on those problems. I don't recall if I answered the question, but
Thank you.
two-adic patterns, why specifically two-adic patterns? Well, just when you see parity patterns, you want to know, well, is that the full story? Is it just mod 2? And then you look at other moduli and you notice mod 3, 5, 6, 7, 9, 10, and so forth don't look nice, but there's these patterns, mod 2, 4, 8, 16, etc. And something's going on here. Something requires explanation. But as to why these things exhibit two-adic patterns and not other kinds of patterns like mod 3, I really don't know.
Yeah. Are there any more questions? Okay.
I guess let me comment here that there are tiling questions where you get powers of 5, unlike the Aztec diamond problem, which is powers of 2. So one interesting topic might be to look at the kind of counting problems on graphs where you see powers of 5 and look for 5-adic continuity properties of some kind. I don't think anyone's done that. So maybe 2 is only special because we're looking at certain kinds of problems and other sorts of p-adic analysis are relevant to other counting problems.
Okay. With that, we will thank Dr. Propp. And I'll stop the recording, and if there are any questions, you can ask after.